Let's start with the first example of beams with continuous lateral support. The first example, design a 7-meter long, simply supported I-section beam subjected to service live load that is 5 kilonewton per meter and imposed dead load of 6 kilonewton per meter. Okay, as shown in the figure below. Okay, here you can see the 7-meter long beam and UDL is applied. Okay, the next line is the compression flange is continuously supported. It means the flange, uh, the uh, the section flange is continuously supported, means either embedded in the concrete or with the shear connector is connected with the concrete slab. So first, basically this problem have two parts. One is you have to use A36 steel, means FY 250 megapascal, and second when you will use the FY 345 megapascal, and the permissible live load deflection of span our span our 454 345 megapascal steel. And the allowable criteria for A36 steel is L over 360, and for 345 grade the author has given the permissible live load deflection is span over 450. So let's start. So first of all, for the designing of the beam, we do not know the section self weight. For the calculating of the loads, we do not know the self weight, so we will assume the 10% superimposed dead load. Here our dead load is here 6, so 10%, that will be 0.6. so here our total factor load 1.2 dead plus 1.6 live, 1.2 dead, that will be 6.6, that 6% of self weight that we have assumed. So 1 plus 1.6 live load 5, so our total factor load that is 15.92 kilonewton per meter. Okay, so when you will solve, you will get the reactions, you will get the shear force diagram and bending moment diagram. So after analyzing, we get the maximum shear force that is 55.72 kilonewton and the maximum moment that is 97.51 kilonewton. Now we have to design this beam against bending moment, against shear, and we have to check the deflection criteria one by one. First of all, for bending, now our beam is continuously braced, means our flange is continuously supported. Oh, so our CB value will be 1, so no need of modification. So here is our moment and shear force. Compression flange is continuously braced, we know. Okay, so assume the section is to be internally compact, and knowing that there is no lateral torsion buckling, means first of all we are assuming, but later on we will apply the checks that there is no lateral torsion buckling. Okay, and if there is, then we will use the moment capacity accordingly. Okay, so here is the criteria. Required plastic section modulus, applied moment divided by stress, that is 250 megapascal, means this is the required section modulus, plastic section modulus against this 97.51 kilonewton meter moment. So first of all we are going to design the beam for moment, then we will check for shear and then for deflection criteria. And the here is the minimum depth check, that for A36 steel, that is 7000 over 22, that we have discussed in the lecture. So our minimum depth is 318 millimeter. So whatsoever we will pick the section, our section plastic section modulus should be greater than this, and our depth of the beam should be greater than this, and it should be minimum weight. So selection of the beam will be based on this criteria. So whatsoever we will select the plastic section modulus there of that section should be greater than the required, should be greater than minimum weight, should have minimum weight, depth should be greater than T minimum. So now we will consult the design aids. Okay, so that is also given at the end of this book. Okay, so here separate design aids. Okay, now I will go in the design tables. Okay, beam design table. So I will just name the page number for your easiness. First of all, let me find. Here is a column tables. Okay, here is LRFD beam selection table for A36T, WS and M shapes. Okay, so here I will rotate it. Okay, so now here is a section modulus. Our required section modulus, that is 433 to 10 raised power 3. Here is 10 raised power 3, that is our 433. That is too much, so I have to go down. Here is 354, I will go up. Here is page number 166. So what required is 433. So here is 426. Here is 433. Here is 446. That is greater than 433. But check, you are seeing that there is a bold above the each row, each group of rows. There is first line that is bold. Okay, so it is all automatically giving that please select the bold section that have minimum weight. That's check. Our required section modulus, that is 433, but here you can see 446. But when we pick 446, its weight is 41 kg per meter, 0.7 kg per meter. And if we pick 480, whose section modulus is greater, so but its weight is less, 32.7. But the next issue, that is the depth. Its depth is 310 millimeter, but our requirement is greater than 318 millimeter. So here, so in the design aid, 310 32.7 is good, but its depth is little lesser than our required. So we will move further up. Okay, 310 to up, we will pick this section 360, that depth is greater than 318 millimeter, whose plastic section modulus required is greater than, okay, minimum weight. You can pick 46, 38, but our criteria is we will go for economy and 32.9. So 36, 360 into 32.9. Okay, so here new section 360 32.9 is picked, 54 into 10 raised power 3. So for now we will perform the compact section check, means there is no lateral torsion buckling. Web is continuously connected, means web is continuously connected with the flange. That criteria is okay. Now flange local buckling criteria, BF over 2TF, that is again 7.5, is less than 10.7. I have highlighted in the lecture, that is 10.7 for the A36 steel. For A36 steel, H over TW 53.3, that is again less than lambda P, LP, lambda P. So our section is internally compact. Okay, so now for moment capacity formulas, our section is continuously braced, so LB is less than LP, and CB equal to not included will be used 1. Why? Because there is no our member is continuously braced, so no need of modification. So moment capacity formula, first case will be used Zx Fy divided by 10 power 6 multiply with factor, reduction factor. Our moment capacity is 122.4. So our applied load is 97 something, 97.51. So our capacity is greater than, so its check is okay. Now we will go for shear design. Okay, for the shear design, there is a check if our H over TW is less than 63.4, then shear yield criteria will be applicable. Okay, here. So now CV1, CV value will be used 1, and that I have discussed in the lecture. So here 0.6 FYAW, that is the depth of the section, and depth of means height of the web into thickness of the web, AW. So our shear capacity is 303 and the applied shear, that is 55. So our capacity is greater than the applied shear, so our this check is also okay. Now delta actual, our in this beam, our UDL is on the beam, so we will using the direct formula 5/384. WL is the live load, that is 5 kilonewton. Sorry, WL is service live load, that is 5. Okay, here 5 is used. Okay, so 5, and L4, that is in millimeter. Okay, and you got the deflection value is 9.42 millimeter. So allowable deflection for A36 steel, L/360, 7,000 divided by 360, 19.44, that is much more. So our actual deflection is less than the allowable, so our this design check is also okay. Now for self weight, previously we have assumed, now we have the actual self weight, that is 32.9, multiplied with 9.81, we got into kilonewton, that is 0.32. We have assumed 0.6, that is greater, so it's okay, but you can revise, it's up to you. Okay, so now our all checks are okay. Moment capacity check, shear design check, or and deflection check, all checks are okay. So our final design section, that is W360 into 32.9. Okay, so our first part of the example is clear. Now in the second part we have to use 3345, and we have to put each values. For example, we are using the direct lambda p, but for 345 we have to calculate that for each case. Okay, and here previously we have used 7,000 divided by 22, that is for that is for A36 steel, and for 345 the value is, after putting the value of Fy, we got the 7,000 divided by 16. Okay, that is D minimum. Our D minimum is for 38 millimeter, and our Z required 314 millimeter, 314 10 raised power 3, depending upon the moment. And now grade we are using 345. This D minimum is much larger, means the section depth is too large. So we will use the direct deflection criteria. This is D minimum trial criteria. So we will use the direct criteria here. You can see this is the deflection calculation formula 5/384 if the UDL is present. So here is the allowable deflection for 345 grade. So that is L/450. Then we taking all the values on the other side, we have all the data. We do not have the I cross moment of inertia. Here we get on the other side, here is the I required moment of inertia 5024 into 10 raised to the power 4. So now for the selection of beam, we will also consider the moment of inertia. Means we will check moment of inertia, Z, and minimum weight. Moment of inertia, I should be greater than whatsoever beam you will select, its I should be greater than this. Weight should be minimum, and Z, whatsoever you will select, that will be greater than Z required. And the rest of the criteria will be same. You will pick the beam, okay, and whatsoever the beam, but whose I should be greater than the required. Okay, then you will perform the compactness check, then you will go for the moment capacity, then same way you will go for shear capacity check, allowable deflection check, and at the end you will write down the design section. If any check fail, you will go for revision, means perform second trial and pick the higher section. So that's all for example 1. Have a nice day.